Okay, here we are. We're going to do some work applying what we've done previously on equilibrium constants to what we're doing right now in acids and bases. So in this video, I'm just going to talk about ionization constants for acids, and then there'll be another video for bases. I'm on page 231 of your notes, so if you would turn to those, I'm going to go through this relatively quickly, so if you want me to go through it slower, you're just going to have to stop and start the video, but otherwise the video gets too long. Reviewing, we talked the last day about how some acids are classified as being strong acids, and that's ones that will completely dissociate in water. Others, and the ones that we're more interested in this unit, are weak acids, and they're the ones that don't completely dissociate in water. So at the top of your page, there's an equation there. There's our old friend hydrofluoric acid, a nasty acid in itself, eats glass and all kinds of stuff like that. It's a weak acid, so looking at that equation, you should be able to pick out what the Ka is. And if you said that the Ka is going to equal the concentration of hydronium ions times the concentration of fluoride ions over the concentration of hydrofluoric acid, you'd be correct. Once again, let's just remember that water has a constant concentration of 55 molar, so because it's constant, it's rolled into the constant for the Ka. The stronger the acid, the higher the value for Ka. Okay, now let's go to some examples right now of problems that we can do. Sample number 1, we take acetylsalicylic acid, that's also known as aspirin or ASA, that you might see it in the store as ASA, is a weak monoproduct. We haven't really talked much about that, but monoproduct means that it's only going to lose one hydrogen. If it was diproduct, it would lose two, like in sulfuric acid. Anyway, this is a monoprotic acid, which can be abbreviated as HASP because I don't want to write it all out all the time. A 0.1 molar solution has a pH of 2.24. Calculate the acid ionization constant. Well, hopefully you'd say, okay, what's the first step? Let's come up with an equation. So let's use the short form HASP, and we're adding it to water. Draw your equilibrium symbol, and what's going to happen here is my proton is going to be donated to the water, so I'll get H3O plus, and I'm going to also get ASP minus. I would write my Ka expression, so once again you're well versed in that, hopefully. Certainly on your mid-year exams, equilibrium constants were well done, and if we do that, there's our equilibrium expression. So now what we need to do, being that we're trying to find an equilibrium constant, is we have to find values for this. Well, what did we do previously? Well, you might recall that we built a table. So let's just do it over here on the left-hand side of the page. So I'm going to get the concentrations of my three species that I'm interested in. I'm going to use short forms for initial, change, and final. My problem says that I start with a 0.1 molar solution. These are 0. Now what do we do? What other information do we have? Well, if we look very closely, we see that the pH of the solution in equilibrium is 2.24. So that will give us our hydronium ion concentration in the final amount. Well, if pH is 2.24, how do we calculate the hydronium ion concentration? Well, hopefully you recall from the last lesson that our hydronium ion concentration will be 10 to the minus pH. So subbing in, we get 10 to the minus 2.24, and so our concentration is going to be somewhere around 10 to the minus 2. Remember, in terms of significant figures, if there's 2 decimals in my pH, my value should have 2 sig figs. And if I do the math on that, it's a very small number. It's going to be quite a bit smaller than this. And I'm just going to go to my calculator and do that. So 2.24, I change the sign and then do the inverse of log, and it's 5.8 times 10 to the minus 3. So if I look at that, it's really equivalent to about minus 0.006 because I only have 3 decimals here. This is, I'm going to keep the number here though, 5.8 times 10 to the minus 3 and 5.8 times 10 to the minus 3. Those are positive. So I end up with those exact numbers in my final. And here I'm going to have 0.094 molar. So let's put those into my Ka expression. Hopefully you recognize that we should get 5.8 times 10 to the minus 3 squared over 0.094. Let's just call that 6. 6 times 10 to the minus 3 squared is 36 times 10 to the minus 6, or 3.6 times 10 to the minus 5, and divide by 0.1. It's going to be about 3.6 times 10 to the minus 4. 3.6 times 10 to the minus 4, and there's our number. Oh, I'm sorry. I was working off the camera. I do that quite often. Anyway, there's our number, and that's all using stuff that you've done previously. Okay, I'm quickly going to go into sample number 2. Unfortunately, there's been a bit of a formatting error, so the second problem runs into page 232. Sample 2, ascorbic acid, also known as vitamin C, is a weak monoprotic acid, which can be abbreviated as HASC. Okay, where are we here? There we are. And it has an acid ionization constant of 8 times 10 to the minus 5. Calculate the pH. So this time we're going in the other direction. Similar start with an equation, so plus water. Put in your equilibrium sign. We're going to get, whoops, sorry, I don't know why I did that, but plus H3O plus. My equilibrium expression for the constant is going to be the concentration of H3O plus times the concentration of ASC minus over the whole concentration of the acid. Once again, I'm going to start with my table. Initial, change, final, 0.100, 0 and 0. But now what do we do? This time we're given the equilibrium constant. So if you recall, we have to work with some unknowns. So we're going to say here minus x, and if that's going down by minus x, then these are going up by positive x. So I have x and x, and 0.1 minus x. Putting this into our equation, I have 8.0 times 10 to the minus 5 equals x squared divided by 0.1 minus x. Now, this is going to lead to a quadratic formula. Do you remember how we can get around that? Okay, I'm just going to go down here, lower in the page. If you take the value that you're adding or subtracting x from, in this case it's 0.1, 0, and you ratio it to the equilibrium constant, this is going to be a number that's greater than 1,000. I think it's about, I would say it's about 1250. And therefore we can say that 0.1 minus x approximately equals 0.1. Okay, and you have to show that step. Okay, so let's just go back up here. I'm just going to say this equals 0. We can now very easily answer this question. X squared equals 8.0 times 10 to the minus 6. Well, the square root of 9 is going to be somewhere around 3. Sorry, the square root of 8 is going to be somewhere around 3. Let's just call it 2.8. Square root of 10 to the minus 6 is 10 to the minus 3. And normally I would say, hey, that's great. However, it's said to calculate the pH of the solution. Okay, so the pH of the solution, we're not done yet because X is actually our hydronium ion concentration. I would encourage you to keep writing this equation so that you memorize it. Okay, and then if I plug in my number of 2.8 times 10 to the minus 3, the log, or negative log of minus 3 is 10 to the minus 3 is going to be 3, so it's going to be somewhere around there, and we have 2 sig figs, and I think the number will be, let's see, what do I got here, 2.55, and hopefully you got the same thing. Okay, you'll see at the bottom of the page there's some homework questions, and notice I've put the answers no particular order. Please have those done for when I return next day. Thanks very much and good luck.